Hello, and welcome to this video on what is y equals e to the x. This is a function that you can see on your calculators. And what we're going to investigate is what actually is it. So to start with this, we're going to look at GeoGebra. GeoGebra is a free application that's available online and really worth using. So just going to this, I'm going to show you to start with this here and to show you where it all comes from so you can find it in GeoGebra. It's under exponentials and logs, and the author is Catherine Peake, so thank you to her for putting this on so that we can all look at it. So do use what's available, it's free to everyone. And what you'll notice here is the function e to the x. And before you've watched this video, you should already be aware of what 2 to the x is, what 3 to the x, what these graphs look like. And this here is the graph of e to the x. And we're going to look a little bit later on what actually e is. But it is special. And what makes it special is explained in this graph. If we look at this point P on the graph of e to the x, the x-coordinate is 1.42. The y-coordinate is 4.137. And that is the same as the gradient, because remember, the gradient is the change in the vertical divided by change in the horizontal. So we've drawn a triangle. So here's our tangent. We've drawn a triangle. And if we notice 4.137 divided by 1 is 4.137. So this gradient of this line at 1.42 is the same as the actual value for y. So what happens at other points? So let's try here. We have that x is 1.947. My y value is 7.006. And here, my gradient again is 7.006. Does this happen that y and the gradient are the same everywhere? Let's have a look. Yes, here my y value is the same as my gradient. What about here? Again, they're the same. Again, they're the same. So what we're finding is, whatever this e is that we don't know, as we move along, the y value and the gradient are always the same. So that makes it a very special function. So going back to here, what does this tell us? Well, it tells us that the gradient, which is dy by dx, remember, the change in y over the change in x, is equal to y, because the gradient on that previous graph, and go back and look again if you need to, the gradient is the same as y. So dy by dx is the same as y. So that means that when I differentiate y, I still get e to the x. And that's the real thing to really take away, is that e to the x, when differentiated, is still e to the x. Because the y value is the same as the gradient. So the y value is the same as dy by dx. So repeating that again, because it's really key to understand that, when you differentiate e to the x, dy by dx is e to the x. Now I would write that down so you can actually see that. So y equals e to the x, dy by dx equals e to the x. So the next and obvious question is, well, what's the value of e? What is e? And again, we're going to use more GeoGebra, and this is something that I put together. So going back to where we were, and you can go onto GeoGebra. It's a fantastic product, and you can actually look up what you can do on there. You can use it like a graphical calculator if you don't own one. And you can actually investigate graphs, many other things as well, but particularly I'm interested in investigating graphs. Now here, what I've set up is this green line at the moment is 2 to the power of x. And this red line here, this here is actually the differential of 2 to the power of x. At the moment, I wouldn't expect you to know how to work that out. What we're focusing on is finding out about this magical number e, because I do think it's magical. I think it's absolutely wow that there's this function that when I differentiate it, it has the same answer as the original function. So if we look at this, the green line is 2 to the x, and this is my differential. Now, if these two lines sit on top of each other, we then know the function and its differential are the same. And at the moment, they don't sit on top of each other. So what happens if I take it this way? As you can see, I've moved that a little bit too quickly. Here, a equals 1.6. They seem further apart. If I move them back towards 2, you see, and they're slowly getting closer and closer together, but they're not quite meeting. So I know that going this way for my value of A, and by the way, my value of A, this slider I have, you'll notice I've moved this to 1.6. This alters this green graph to be 1.6 to the power of x. And this is the differential of that. And this is what makes GeoGebra so fantastic, because you actually can see it happening. So as I move this way, you can see it's getting further and further apart. So I don't want to go that way. As I get to 2, it's getting closer and closer together. So what happens at 2.2? I'm 2.3. Still not quite there, but can you see they're getting closer? 2.4. 2.6. Are they on top of each other? Don't know. What about? Oh, that's it. 2.7. At that point there, my red line and my green line are on top of each other, which means y equals f of x and y equals f dashed of x look like they are the same curve. Now, if I zoom in, I don't know whether I can zoom actually in enough, but they actually aren't quite on top of each other. I think I'd have to go a lot smaller to make you see this, but they are fractionally out. And I think you're starting to see, and you see, if we really zoom in, not quite. And that means that actually this number, 2.7, is good to 1 decimal place, but actually this value of E has more decimal places than just 1. So what is this magical value of E? Well, the magical value of E, let's go back to our PowerPoint now, is actually 2.7182884590345235360287471352 and more. So this number just keeps going. Have we ever met a number like that before in maths? A number that just keeps going, where there's no pattern. And remember, this number is to the power of x. And you can now see why we've given it a letter E, because actually writing that out wouldn't be practical. So therefore, it's been given this value E. And we have met something like this before. We've met pi. And if we look at E is irrational. and is a constant value. It's always that value. So just like pi is irrational and it's always the same value. It doesn't change. And the reason I've written that there is it can be very easy because we write e that we're taking it as a variable. It's not a variable, it's a constant. Now, another thing to know about e, which you may not have met yet, is that e is the natural base, we call it, for logarithms. And we often write this as ln, and 8 is just a value I've chosen, rather than log to the base e of 8. But by the way, both are acceptable. You may have done some work on logarithms before, but here you may have been using a base. For example, 10 is a very common base and is often found on a calculator. This ln, again, which is often seen on a calculator, that's using the base, and that's the natural base e. So this is our value for e. And remember, what's particularly special about it, if we go back a few slides, is that when we differentiate it, e to the x differentiated is still e to the x.